Lecture 10, Virtual Memory. Okay, even as we've discussed some of the things that build our way up to virtual memory, we've still got a couple of things to consider in how we want to make this work. And one of the things that we will face is, well, pushing our system to the limit. Okay, so paging is good. Even with moving pages into and out of memory, there's a limit on what we can do with the system, right? Specifically, a program that requires more memory than the physical memory cannot run. Okay, maybe that sounds kind of ridiculous. Maybe you could think, well, I have 16 gigabytes of memory in my system. Shouldn't that be enough? For any program, that seems like a lot. Could we make do with that? The answer is, well, usually, but it varies by what program you want to do and your workload. But it's not just for desktop systems, right? A server or a supercomputer machine that could be working on a very large data set might require more memory for a specific application than is available in the machine. Moreover, when we have many programs running in a multiprocessor system, we could easily have a situation where the sum of memory requirements, that is, demand for memory, exceeds available memory. Okay. It is less than ideal to have a processor waiting for something to do, because a process that is otherwise ready to run is unable to proceed because there are just insufficient free frames in memory at the current time. And the problem that we're facing here is this idea of all or nothing. That is, a process must be entirely in memory if it's going to run, and if it's swapped to disk, the whole process is swapped to disk. That's kind of a painful restriction, right? In a lot of cases, the entire program is not needed at any given time. We discussed already this idea of something like a 90-10 rule in the subject of caching, which is to say, the common path is needed most of the time, and occasionally we'll need some error handling code or some special situation handling code, or just things that happen periodically. If your system has a month closing procedure and it's used to close out the previous month, well, you do that at the start of the next month, and then you don't need it again for another whole month, right? That's a very long time even for people. So, this is painful. Similarly, code that's used to start up the application is needed at the beginning of the program, but it's never needed again on that run, right? Next time the process is started, maybe, but not again in this current execution. Data structures, collections, buffers, those kinds of things can be declared to be very large, even when that's not actually needed. For example, array list in Java, I pick on Java because it's a subject I know a bit about, is by default 16 elements, even though you don't necessarily plan to put 16 elements in the array list. Maybe you're only going to need 4. That could totally happen, right? They tend to be larger than is actually needed because it's less painful to ask for a bit more space at the beginning, even if you don't need it all, than it is to try to resize or grow the collection as the situation demands. So, yeah, we have some wasted space. If we could find a way to execute programs that are only partly in memory, we would get some interesting benefits. 3 of them listed here. Number 1, a program is no longer constrained by the size of physical memory. You can just use the entire virtual memory space without having to worry about whether it fits or not. Okay. Number 2, each program could use up less physical memory, allowing more processes to execute concurrently. So we don't have to keep in memory code we're not going to use, or space we're not using, or any other pages that are otherwise taking up frames. And number 3, that would also imply less I/O is needed to swap user programs in and out of memory. Right? That way we don't have to swap in a whole program. We just swap in the parts that we need, and we're ready to go from there. Does this sound familiar? Good news, everyone, in the words of Professor Farnsworth. We've already discussed many of the key ideas to making this work. If you were wondering about why did we talk about caching immediately when we did as the previous lecture topic, now you know. It's because, well, caching is the solution to the problem that we have here. And you can think of main memory as just another level of cache, level 4 or level 5 cache, and the disk is just the last stop where data can be. So if a page is referenced and it's not currently in main memory, it's a page fault. We go get it from disk and we put it in main memory. A page might need to be evicted from main memory to make way. Okay, so we have a page replacement algorithm to write it out, just as we talked about when we were covering caching, when we were thinking about CPU caching. Well, the same applies by treating main memory as a cache for the hard disk, which has the balance of the memory that we need. Okay, this diagram kind of gives an interesting approach. It says, okay, for a given virtual memory, we have some number of pages, and when we want to reference one of them, well, we'll look in the memory map. If what we need is present in physical memory, in RAM, we'll just get it. If not, it's page fault, and we have to fetch the data from disk and load it into memory somewhere, and we'll update the memory map accordingly. Our typical approach like this is that of caching, which is demand paging, which is we don't load something into the cache until we have a reason to, until it's requested, until we think it's needed. We don't really do predictive operations in this case. This prevents unnecessary disk accesses. This is sometimes called the lazy approach. Lazy is typically an insult. If my parents told me that I'm lazy, they didn't mean it as like, oh, you're so efficient in avoiding unnecessary work. But in the case of computers, it doesn't necessarily mean anything bad. It just means we only load it as late as possible. We load it when we need it, and only when we need it. We're not proactive about this. As you can imagine, the goal is to go to disk as infrequently as possible, because disk is, from the perspective of the CPU, extremely slow, right? Anything we can do that avoids going to disk is greatly appreciated in terms of execution time of our program. In fact, disk is so slow, it means we can get into a state called thrashing. And Tom Hardy looks rather displeased in this regard, and you should too if you were experiencing thrashing. Mad Max Fury Road, well, it was a visually interesting movie. It's yeah, I mean, this channel isn't about movie reviews, but it is fun. It is fun to think about. Anyway, so what is thrashing? We're going to talk about it in some more detail a little bit later on, but thrashing, if you want a quick off-the-cuff definition, just says the operating system is spending most or all of its time swapping pages in and out of memory so that very little actual work can get done. Right, we're spending all of our time moving pages, reads and writes, and blocking processes while they wait for the reads and writes to resolve, and that's not great, because that's not useful work, right? It's necessary for work to get done, but our preference, all things considered, would be to not have to swap pages in and out at all. So we'll make the best of what we've got. Now, apparently, I read about this at some point. The next operating system, as in like next step, which was one of the three parents of Mac OS. The Mac OS is weird. It has three parents. One of them is the classic Mac OS, the ancient one. The BSD, which is a Unix-like system, and Next Step. Next being the company that Steve Jobs went on to found after he left Apple. So things get complicated in that regard. But in any case, Next Step machines, if they were booted on a machine that had only 2 megabytes of RAM instead of 4 megabytes, the steady state of the system would be just a constant level of swapping to and from disk. This is particularly bad because the most common cause of failure in the Next boxes was the hard disk drive. They needed to save money somewhere, and they chose a cheaper drive. Where did the money go? Well, they had cool magnesium cases. So after they died, they at least made impressive conversation pieces and or door stops. When I was a kid, my parents would refer to like old computers as door stops because they would get out of date so quickly you couldn't use them for anything else except maybe boat anchor. Okay. history lessons aside, you'll learn a lot of history in this course, I think. With virtual memory, right, each memory reference involves potentially a 6-step process, right? We need to check if the memory reference is valid or invalid. If it's invalid, it's segmentation fault, terminate the program. And if it was valid, but the page reference is not in memory, then we can retrieve it. And we'll find a free frame or make one by evicting a page. We'll request a disk read and possibly write to bring in the new page and optionally write out the old one that needs to go. And when the disk read is complete, we'll update our records, so the memory map, make sure that we have everything up to date. And then we can restart the instruction that referenced the page. So this diagram is a little bit confusing, so I gave you the breakdown on it first before I try to explain it. But if we have a reference and we look in the page table, maybe it's there. If it is, great. If not, we have a trap to the operating system that says, hey, please fetch me this page. So the operating system will schedule fetching the page, bring it into a free frame, update the page table. I don't know why it says reset. Reset kind of implies, have you tried turning it off and on again, or clearing it or something, but we're just updating it. And when that happens, we restart the instruction. And so between steps 4 and 5, as you will imagine, a significant amount of time takes place, right? While we're waiting for the page to arrive, and this will at least be the cost of a disk read, and potentially add to that a cost of a disk write, so that we make space for it. Okay, when we do that, hopefully the processor is doing something else, right? It shouldn't just be sitting around doing nothing. That's kind of inefficient. And in the meantime, we should be working on something else. You'll notice I talked about this idea of restarting an instruction. Start again. Nice day for a white wedding. That's a key requirement. We have to be able to restart any instruction, and if we can't do that, we have a problem. Right? We save the state of the process, including all the registers and the instruction pointers and everything, when the page fault occurs, recognizing that we're going to have to restore this state later. And when we restart the process exactly where it was, we want to redo the instruction, and then we're going to hopefully succeed, because the page that was needed is in memory and is accessible. So page faults could occur basically at any time. Bad things could happen to us no matter what we do here. That includes fetching the next instruction, right? If we fetch the next instruction and it's a page fault, we wait for that page with the next set of instructions to come in, and then we can proceed. That's fine. If a fault happens when we're doing an operation that required fetching an operand, where we said, we want to add this to that, then we fetch and decode the instruction again, and we fetch the operand. So we might actually end up repeating a little bit of work, right? Losing one cycle to repeatedly fetching and another cycle to repeatedly decoding the instruction is fine, right? The cost of it is very small in comparison to the cost of having the page fault in the first place. So a little bit of work might actually be repeated, but it's not anything we should lose sleep over. When we talk in the future course about speculative execution in the CPU, if you take, say, ECE 459, I am legally required to advertise it every X amount of minutes, so here you go. Then there's going to be wasted cycles anyway, because there will be speculative execution where the CPU imagines, I think this is going to happen, and if it's right, yay, and if it's wrong, it's wrong. So we don't lose sleep over a couple of wasted CPU cycles. But let's imagine then we have a pretty simple add instruction that adds A to B, stores the result in C. So we have to fetch and decode the instruction. The instruction tells us about what are the operands, and we have to retrieve the operands, then we add them, and we store the result in a target location. If a page fault occurs when we're trying to do the write at the end of the instruction, we might end up restarting it, so redoing the fetch, redoing the decode, redoing the retrieval of the operands, and then we do the addition again. Then finally we can write it into the target location. right? That's kind of a worst case scenario, that if the write is the one that causes the problem, then it results in redoing the maximum amount of work. But the number of steps required to do an add, as I say, is not overall very large. It does depend on your CPU. So work is repeated, including redoing the addition, but that actually maybe should worry us a little bit, right? Does it? Right? There is a distinct possibility that if our paging or our cache replacement algorithm is not nice, when fetching a page containing C from disk, the page that contains A or B could get swapped out, meaning that the second run of the instruction will also produce a page fault. That's kind of unlikely if we have chosen a sane replacement algorithm, because the page containing A and B will have just been referenced and therefore are unlikely to be evicted. But if you chose something like first in, first out, or random page replacement algorithm, you could actually get this behavior, and then you would probably be annoyed, right? That's not good. It is hypothetically possible. It is... I mean, you can imagine other nightmare scenarios where, you know, the page containing A is constantly replaced in memory and cache by the page containing C, and vice versa, because you hash the page and, you know, they both turn out to be the same location. But a system vulnerable to this problem has, should we say, significant design issues to begin with. Okay, here's the problem. Sometimes there are no do-overs, right? The idea of restarting every instruction sounds nice, but there isn't a guarantee that you can restart every instruction without any side effects. An example of the situation is when an instruction modifies more than one memory location. If we're moving a block of, say, n bytes, so we're like doing a mem copy from one location to another, it's possible that those bytes straddle a page boundary. Which is to say, like, half of the array is in page X, and the other half is in page X plus 1 at either the source or the destination. Okay, now in a simple scenario where, you know, the source and the destination don't overlap, there's no problem. We can just restart the copy and there's no problem. However, if the source and the destination overlap, we're trying to like shift the content of the array, you know, left by one element or right by one element or something like that, then we might have a problem, right? Because if we completed part of it, but not everything, we've now left the array in some inconsistent state, and restarting the operation from the beginning will now copy the wrong data from one place to another. So that's not good. We would like to avoid that situation as much as we can, because, you know, the move operation was requested. And one of the solutions for this is to try to access the start and the end addresses for a bulk operation before the move begins. If one of the pages is not in memory, the page fault is triggered before any data is changed, which ensures the move will succeed when it actually starts. Another solution is to use some registers temporarily to hold overwritten locations so that we can always roll back the changes if that is necessary. Things are complicated at this level, right? If a page fault occurs, the temporary data is restored so the instruction can be restarted, and, you know, everything goes back to the way it was. But it does get kind of complicated. You can think of other strategies that involve, well, if we had the pages loaded into the CPU cache and we modify them partly only in the cache, we can throw them away and just reload them from memory, but it's not easy. Okay, let's also talk about the performance. And as we've already seen, finding something in cache is, you know, significantly faster, if you will, than finding it in main memory, and retrieving it from disk is dramatically slower. And in the previous topic where we talked about cache, we had an effective access time formula that considered cache as well as main memory, but not disk. And so what we'll do is we'll just expand on this. If you remember, H is the hit rate in the cache, and 1 minus H is the miss rate. T sub C is the time to retrieve something that's in the cache, and T sub M is the time to retrieve something in memory. And if we just looked at the memory and disk interactions, and we had something like this, we would replace T sub C with T sub M, and replace T sub M with T sub D. which is the time to retrieve it from disk. And if we said that p is the chance that a page is in main memory, if we have a cache miss, our effective access time is p times t sub m, so the chance that it's in memory times the time that it takes to retrieve it from memory, plus 1 minus p, the chance that it's not in memory, times t sub d, the time that it takes to retrieve it from disk. But of course, that's only part of the picture. What we actually need to do is combine it with our existing cache disk read formula. So then we end up with what we see here, which is h times t sub c plus 1 minus h times, and then in parentheses, the effective access time we just saw on the previous, p times t sub m plus 1 minus p times t sub d. So this represents one level of cache. I mean, if you have different levels of cache, you need to expand the formula as appropriate to make sure that we are including all of the different levels with their hit rates and their access times. But it's a start, right? This is a good estimate to begin with. Of course, to know the actual values here, we need to have a figure for t sub d, but this is a pretty easy quantity to measure, right? We can just expect to estimate that as somewhere on the order of 10 milliseconds in a worst case scenario, just because of the nature of magnetic hard drives. We'll talk about how we get to that number later on, but for now you can sort of just take my word for it. In any case, we expect that p, the chance that something is in memory, to be very large if our paging algorithm is any good. Otherwise, our performance is acutely terrible. Handling a page fault is now merely a simple 16-step process, with some parts. So you can see, I think, why we want to avoid it. And so I've broken it up over a few different slides. But basically, step one is trap to the operating system, save the registers and process state, identify this interrupt as a page fault, and check if the page reference was legal. If so, we'll find out where it is on disk. If not, then we can just end execution here because, yeah, the segmentation fault or something like that. Sadly, no, the Emperor does not say, I will make it legal. Then we have to find out where to place the page in memory using the replacement algorithm. Is the frame we've selected currently filled with a page that has been modified? If so, then we schedule a disk write to flush it out to disk. If not, we can skip some steps and go to step 11. We'll wait for the disk write to be executed. CPU can do something else in the meantime, receive an interrupt when the write has completed. And then, yeah, we were doing something else, so we need to put that down so we can resume handling this, this page fault. So we'll update the page tables to reflect the flush of the replaced page to disk, mark the destination frame as free, issue a disk read to transfer the new page to the free frame. Again, while we wait, let the CPU do something else, receive an interrupt when the disk is completed, save the registers in the state of whatever we were doing in the meantime, update the page tables to reflect the newly read page, and then finally we can restore the state of and resume execution of the process that encountered the page fault, restarting at the instruction that was interrupted. Okay, that's a lot. The slow step in all of this is the amount of time that it takes to load the page from disk. Right, restarting the process and managing memory take 1 to 100 microseconds, we estimate, right? So like 1 microsecond to 100 microseconds. It's for the computer a while, but it's not too bad, all considered. How did I mention sort of the 10 milliseconds or 8 milliseconds figures earlier? Well, hard drives can have a latency of 3 milliseconds and a seek time of 5 milliseconds. And these figures are based on like the mechanical components of the hard drive. So we'll talk about those when we get to disk in more detail. And transfer time is 0.05 milliseconds. So latency plus seek time is the limiting component, and it's several orders of magnitude larger than any of the other costs in the system. And this is the request time for one request, keeping in mind that requests may be queued, so we might have to wait a little bit longer for it to be our turn. And because we're talking about milliseconds here, as opposed to memory access is being measured in nanoseconds, we can see that yeah, this T sub D term really dominates the access time equation. If memory access could be estimated in like a simpler way where we ignore cache, we ignore memory, you get kind of a pretty good estimate by just saying it's 1 minus p, so what's the chance we have to go to disk, times 8 million. And that produces a result in nanoseconds for the average effective access time. As you can imagine, if the page fault rate is very high, performance is very slow. Now again, when we talk about 8 milliseconds access times here, we are considering, okay, this is a magnetic hard drive, it's not a solid state drive, but again, worst case scenario is being considered here. If the performance of the computer is to be reasonable, something like using 10% of the possible time, our page fault rate has to be very low. It has to be something like on the order of 10 to the minus 6. So that's how many misses that we have. So we really need to find what we're looking for in main memory. And going to disk is inevitably going to happen, but we're going to try to make it happen as little as we possibly can. So now you know why solid state drives, SSDs, are such a huge performance increase for your computer. These days it's pretty difficult to come across a laptop or desktop machine that doesn't have a solid state drive as at least its sort of main drive. Instead of spending time measured in milliseconds to find a page on disk, SSDs produce the data with times that look much more like memory reads, so they're not measured in milliseconds. So things are definitely improving in that regard. And as time goes on, SSDs become cheaper and their capacity becomes larger. And there will come a day when talking about magnetic hard drives is kind of no longer necessary because it's no longer relevant. They're so far in the past that they're not worth talking about. But at least at the time of writing and the time of recording, SSDs make sense as boot drives and primary drives in your devices, and you can certainly have a computer that doesn't have a magnetic hard drive. But when we're talking about large servers, big databases, very large amounts of storage, the cheapest option and potentially the most appropriate option given budget and performance requirements does still require them. So yeah, it's on the way out, but it's not dead yet. In any case, I have to advertise, if you will, for Programming for Performance again. If you take that as a technical elective in fourth year, we'll talk about why SSDs are faster, but not quite fast enough. They don't solve everything. We haven't covered file systems in great detail. That's going to come up a little bit later on. I mean, we talked about the file system interface, which is necessary for using things that we want to use and being able to accomplish things with your program. But there are a couple of things that are sort of worth talking about. Files do tend to come with overhead for file creation and management. And to avoid this, the system can have a swap file or swap partition, which is just sort of one giant file or one block of the hard drive, and the system just like deals with the swap files if it's one big file and not tiny individual files. So when we write some stuff out to disk, it just gets thrown somewhere in the swap file as opposed to having different files associated with every process. I mentioned already this idea of copy on write. I'm sure we talked about it when we talked about fork, and it creates an exact duplicate of the parent process, and that process can replace itself with the exec system call. And it does seem like it's a waste of time to copy the memory space of the parent process if the child is just going to throw that away immediately. And we've also discussed this idea of copy on write to reduce the amount of work that's necessary to make that happen. Okay, now we can think a bit more about how that's actually implemented. So if there's immediately an exec invocation, then the new memory pages for the child are brought in, and we just skipped all the work of actually copying the parent because, like, why? What was the point? But if the child is going to remain a clone of the parent, then, well, initially all pages are shared, but they are marked as being copy on write. And as soon as either the parent or the child attempts to modify the page, a copy is made and the modification is applied to the new copy. All the unmodified pages remain shared, but only the pages that are actually modified will be copied, thus minimizing copying so that there is no unnecessary, no unnecessary copying. Some versions of Unix, notably Solaris Linux, have a called vfork, which skips the copy on write procedure, and the parent is suspended. The child process can then use the memory space of the parent, so that any alterations that the child process makes are visible to the parent when it resumes. It is potentially dangerous, as the child can wreak a bunch of havoc, but it also has some potential advantages where you can just skip, passing data back and forth between the child and the parent. It's not always a great plan, but it is, at least in some systems, an option. This is also very efficient if the intention is to immediately exec and you'll get a new memory space anyway. Okay, so that finishes our introduction to virtual memory as a topic. We're going to continue in the next topic with some more details about how to actually make it all work.